So let us look at now the strain life approach to fatigue. All right. So we have so far looked at the stress life approach. The reason why we need to talk about strain life approach is because in the case of low cycle fatigue, where the component is usually subjected to very high stress levels, and hence it is expected to undergo plastic deformation. When it is undergoing plastic deformation, whatever stress life approach that we have adopted does not work, because you need to worry about the plasticity that is taking place in the material. Right? So in order to be able to understand the strain life approach, we first need to understand cyclic plastic deformation. That means what happens when you have apply cyclic loading to the plastic deformation of the material. Once we understand that, then that becomes much easier for us to follow. Okay. So this is what we would like to pay attention to. This is what we call cyclic plastic deformation. The cyclic, so here let us say this stress strain, you're able to see my pointer, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So here you have a stress strain curve for a monotonic load, right? So you know this is elastic regime, and then the stress is changing as a function of strain, and then you can represent this entire process as epsilon is equal to f of sigma. That means epsilon can be, or sigma is equal to some g of epsilon. Either way we can write. Both of them are acceptable. All right. Now let us say you have this fellow, and now what am I doing? Let us imagine we talked about, let us say I have loaded the specimen up to some plastic deformation beyond plasticity, and then I unload. Usually we discuss what happens when it is completely unloaded. Then you know that there will be some plastic deformation, there will be some plastic deformation, and whatever strain that is recovered is what we call elastic strain. Isn't it? Is this clear to all of you?
Yes,
Let me do it. Yeah. So let us say I am unloading from here. The unloading path will be parallel to this elastic path. So initially I have loaded the specimen up to this value. That means the strain is that. But when I have unloaded the specimen to a zero stress, then the strain, this much strain has been recovered. That means this is what we call elastic strain, but this strain is still remaining in the material. That is what we call plastic strain. Okay. Now, what happens if I continue to load the system? I have unloaded to zero stress, but if I continue to go into the continue go into the compressive regime. That is what we are talking about in this figure here. If you look at this figure, you will see that, let us say this is your sigma OT is nothing but your yield strength in tension. Sigma O represents yield strength, sigma OT is your yield strength in tension, and this is your stress strain origin. You have loaded the specimen and you went into the plastic deformation range up to here, and then you are unloading. Normally, when we have discussed, we only discussed about unloading up to zero stress. Now what I am saying is, what happens if you continue to unload the specimen? In the tensile regime, if you are taking a specimen, if you have loaded it in tension, it would have entered plastic deformation at sigma OT. Instead of unloading it in tension, let us say you have loaded the specimen in compression. When you load the specimen in compression, again, the material will undergo plastic deformation sigma OC. The magnitude of sigma OC and sigma OT will be same, but it is in the negative direction. If you are doing monotonic loading under compression, then the plastic deformation, the yield strength in compression will be equal to yield strength in tension, except for the symbol sigma minus. So sigma minus sigma OC is equal to sigma OT, right? So it will plastically deform here. However, if you are loading the specimen in tension and loaded up to here, and then if you are unloading, while unloading, if you continue to unload, and if you continue to continue the loading direction and go into the compressive regime. Until here it is tension, tensile unloading, and here you have zero stress. And now if you continue to unload, then you get into the compressive stress. What is our yield strength in compression? Sigma OC. Ideally, it should have started yielding here. But what happens is the yielding starts at a little earlier at point A. That means when you are unloading in the compression regime, then your yield strength reduces, right, compared to what it would have been. So this reduction, so suppose imagine you have loaded, unloaded, and again reloaded, again unloaded. You can do this several times, right? So that is something that you would see here. You have loaded the specimen, then unloaded, and again loaded the specimen, unloaded, and so on. You will do so many such cycles. So initially it will be like this. And as you increase the number of cycles towards the end, these points, you will have there won't be much of a difference between each cycle. But at least in the beginning, your at each and every stress reversal or stress of cycle, your yield strength keeps changing in compression as well as in tension. And that is what we call Boschinger effect. So what is Boschinger effect? It tells us that the material yields at a lower stress A in compression compared to monotonic loading when the unloading happens. Is that point clear? Is that point clear? Are there any questions here?
Sir, one
Did you
small
understand the concept at all?
one small question, sir.
Yeah.
When you're saying that unloading, so basically when I'm going to put a monotonic loading, it is going till plastic deformation, right? Not within the yield strength.
No, because I am going beyond plastic deformation. When I am
Okay.
unloading after getting into the plastic deformation, I have unloaded here, but this is
Okay.
my yield strength. I went beyond yield strength and then started unloading.
Okay, and when I unload and when I reach A, so we are still considering that we are still going beyond A also, right? Like
So what I'm saying is, normally this is sigma OT. If you have done a monotonic loading experiment in tension, you would have observed your yield strength to be sigma OT in tension. Similarly, if you have done a monotonic compression experiment, you would have observed your yield strength to be sigma OC. Only compression experiment if you have done, this is the dashed line path is what it would you would have followed. Okay.
got it. Okay.
So you
Sir,
have
one question I want to ask you is that can I ask, sir, if you allow, please?
yeah, please.
Sir, basically, the concept that was taught by you, sir, in the previous classes, what I understand was that any material exhibits, like I would say, resistance to a strain in a better way when is loaded compress, like in a compression. So the theory that you have told us now is quite like visible and understandable. But my doubt is like that: how the like what I mean to say is yield strength in compression is lesser than the yield strength in tension.
I will
Because
explain that. See, when
okay,
you are doing monotonic loading, meaning if you take a specimen, if you do a tensile test on the specimen, then the yield strength that you measure would be sigma OT. Okay. If you take the same specimen and if you do compression, then the yield strength that you would measure will be sigma OC. Please note that the magnitude of sigma OC and sigma OT are the same. If you do non-cyclic monotonic loading. Is that clear? So yield strength in tension and compression are not the same. Sorry, they are not different. They are the same in this material. If you do a monotonic loading, if you do a tension test or a compression test, you will measure the yield strength to be the same value. Okay. Even in such materials, when you are doing cyclic loading, that means you are doing tensile monotonic loading in tension, and then you are unloading, but you are not stopping here. You are continuous to load the system in the compressive regime. That means you have started with tensile loading, and then you started with compressive loading, right? Continued into compressive regime. Then In the compression, the yield strength normally should have been sigma OC, but it does not become, it will start yielding at a lower yield strength than sigma OC in compression. Why is that? That is the question, right? Why does it happen that in the compression, why do we observe a lower yield strength when we do this cyclic loading? The reason for that is here. So the reduction in yield stress may be related to the fact that the dislocations of opposite sign. So you have, what do you mean by plastic deformation? Plastic deformation is nothing but dislocation motion, right?
Right, sir. Right, sir.
Yeah. So when you are applying a tensile load and there will be dislocations that are getting piled up. So during this process, there are some negative sign dislocations. So there is, let us say you have a positive sign dislocations are moving in this scenario. At that time, negative sign dislocations are getting piled up at the grain boundaries. But the moment you apply, you change the direction of the loading. What happens? Those negative sign dislocations which are already piled up during the tensile loading, because they cannot move during the tensile loading because their sign is different, they will find it easier to get activated. Whereas when you are doing pure monotonic compression, you don't have those negative sign dislocations piled up already. Whereas in this scenario, you have a negative sign dislocations are already piled up. The moment you change the load, you don't need to create already some negative sign dislocations are already sitting in the material, and hence it becomes much easier for the material to plastically deform. That is why the yield strength in compression reduces.
That is clear, sir. Thank you for so much. Thank you so much for the explanation, sir. Only
Yeah.
one thing, sir. You have also
Hmm.
taught us that like what I mean to say while you're teaching us the crystalline structure of the lattice and all those things. So at that time you taught us that it depends on how the lattice is like what I mean to say is how the crystalline structure is. Suppose in that way, what I mean to say, if the load in such a way that we try to fill up the gaps or like reduce the dislocation, then the strength of the metal will increase. So this statement that you have made, sir, is that universally acceptable or it's applicable to some particular lattice or some particular structure or in that way I'm asking, sir.
So in a crystalline material, what
Yeah.
happens is, for example, I don't know if I have given you this example. Did I talk to you? So for example, if you are in a forest, okay? Imagine you are in a forest where there are trees all everywhere, and you are running in the forest holding a horizontal bamboo stick. Okay?
Yeah.
When you are walking with that bamboo stick, what happens? A long bamboo stick will hit the trees that are there in the forest, isn't it?
Right, sir.
So if you have more, these forest trees can be seen as grain boundaries, right? So when you have more grain boundaries, you will have more obstruction to your motion, isn't it? Imagine yourself walking with a bamboo stick as a dislocation. Now, if you have more grain boundaries, what happens is these dislocations are going to get impeded. That means the motion is not taking place. Now, if you are not the only guy that are running. Similarly, there's a 10 people with these long bamboo sticks are running, and I am expressing the plastic deformation in the material is as a measure of average movement of these 10 people. Then what happens? Each one of them is moving in different directions, and hence the probability of all these dislocations, all these bamboo sticks getting hit by a tree and stopped being moving forward is much higher. Isn't
Right,
it?
sir. Right,
So
right, sir.
that is what increases the strength of the material. That means you are not allowing the deformation to happen. What do you mean by strength? You have to apply much more load in order to deform the material. Why are you
Yeah.
not able to plastically deform? Because your dislocations are not moving easily. Why are they not moving easily? Because they are experiencing obstacles to motion. These obstacles can be separated, various things. The obstacles could be other dislocations which are coming in the way of these dislocations, or grain boundaries like the trees are like grain boundaries, they are stopping it. When you increase these number of dislocations and number of grain boundaries, the strength of the material increases. Right? That is a universal phenomenon. And of course, depending upon the crystal structure, in certain crystals, for example, FCC crystals, the Smith factor is going to be much higher compared to BCC crystal, and hence the not Smith factor, the number of slip systems are more in FCC compared to BCC. As a result, there is more probability for dislocations to move easily in an FCC material compared to BCC material. That is why it is much easier to deform an FCC material with FCC crystal structure compared to BCC crystal structure. All right?
Thank you, sir.
Yeah.
Right, sir. Got
Yeah.
it.
Any other questions? So, now there are no further questions. So this Boschinger effect, so the stress strain response regarding during the cyclic loading expresses this. There are several complexities. What every half cycle you will have yielding happening, because one cycle means going from here and coming back and going here, right? When half cycle, in one cycle there will be two yieldings, one in tension, another in compression. Thereby every half cycle loading you have one yielding occurring. And what happens is that with each and every cycle, the yield point is changing. Can you see that? So you have started off here. This is your yield strength. And in the next cycle, the yield strength is somewhere here. And in the next cycle, the yield strength is somewhere here. The yield strength is increasing at each and every cycle, so to speak. Right? So now, if the material itself is changing every cycle, what is the meaning of that? You should be able to represent this change in material response with every cycle during a cyclic loading. Because when I talk about fatigue means I am actually doing this reversal, right? Stress reversals, number of times. And at each reversal, my strength is changing. The yield strength of the material is changing. So I need to have a model that can actually describe such change in material response. Here we are showing the stress strain response of an aluminum alloy for 20 cycles with completely reversed strain at epsilon A. That means this is a strain amplitude. Until now, we are talking about stress amplitude. You will realize that here you are actually going from strain amplitude from here to here. If you carefully observe, all this is between these 2 points, right? You are going up to this strain, epsilon max, and this is epsilon min. And you are loading up to that strain and unloading, right? And again loading up to that strain and reloading, and so on. So you are oscillating between maximum strain and minimum strain. However, here it is fully reversed. That means the maximum strain and minimum strain are same magnitude, values or magnitude, but they are positive and negative strain. Can you see that? So now we are talking about strain amplitude. So if you would plot strain as a function of time, we are talking about something like that. This is my epsilon max, and that is my epsilon min, that is in the negative. And this is my strain amplitude epsilon A. Okay? Now, now let us talk about hardening processes. So when we talked about hardening in the previous class, right? So when we are discussing plasticity, mechanical properties, let us say this is a linear elastic material whose slope is E, and let us say this is your yield strength. After the material reaches yield point, then there will be some another slope. That is what we call hardening. Depending upon the type of hardening, the slope may be different. It could be a straight line, linear hardening, or it can be a power law hardening. That means it will not be a straight line, it can be a parabola, and so on. Now, so in materials, during cycling process, you have seen that the yield strength of the material is increasing at each and every cycle. What do you mean by yield strength increasing? That means it is becoming much more harder for material to plastically be deformed. That means there is some hardening that is taking place. So there are two kinds of hardening that happens in materials. One is called isotropic hardening, another one is called kinematic hardening. What is isotropic hardening? Carefully look at this below. So you have loaded this specimen beyond the yield strength sigma naught up to a value called sigma dash. So from here to here, the height is, this distance is sigma dash. Now when you are unloading, if the yielding starts at a distance of 2 sigma dash, that means from here to here sigma dash, from here to here minus sigma dash, that is total is 2 sigma dash. If the yielding starts there, then this is called isotropic hardening. That means the yield, even under cyclic loading, the yield strength in tension and compression are one and the same. And that is not, if that is same, then what happens? In the Boschinger effect, so the yielding will not happen early, it will happen a little late. So that means you will follow the same path. You will not have change in yield strength at each and every point. So this isotropic hardening for that reason cannot represent Boschinger effect. That means it cannot predict Boschinger effect. Now let us come to kinematic hardening. What is kinematic hardening? You go up to sigma dash, and now what is the yield strength in tension? Sigma naught. This one is yield strength in tension. Now from here, if you go by 2 times sigma naught, and that is where the yielding begins, then such a hardening is called kinematic hardening. Right? The distance from here to here, it's 2 times sigma naught, where sigma naught is the yield strength in tension. And that is what is kinematic hardening. So you can clearly see that the yielding is happening much earlier than the tensile yield strength, and hence this will predict the Boschinger effect. Any other questions?
Sir, one small question, why it is 2 sigma not?
Because this kind of hardening is called kinematic hardening. So the idea is, so you are starting here, and now
Yeah.
imagine you are loading the system from that state, right? So you have to see it this way. I need to overcome my tensile yield strength, and
Yeah.
then in the compressive regime, I need to go to the same yield strength. That is why it is 2 times sigma naught.
Okay. Okay.
Now let us look at, so we have these stress strain models, and now we should be able to represent these things in more complicated way. So what are the various rheological models that can represent this stress strain information? Okay. The rheological models used for stress strain representation in elastoplastic response. Now, various elastoplastic models we will look at. This is what we call elastic perfectly plastic. Perfectly plastic means it is easily plastically deforming. Once you reach the yield strength, at that particular strength, if you continue to apply the strain, you will continue to plastically deform. There is no hardening in this material. Okay. So if you have this kind of thing, can be represented by a spring and frictional. This is not a dashpot, but it is a friction slider. What does the friction slider means? When you apply a stress on this material, this particular guy will deform, the elastic spring will deform, but until the stress in the material becomes equal to sigma naught, this guy will not slip. This is what we call friction slider. That means until then the frictional force is large enough to resist the sigma. The moment the value sigma becomes sigma naught, it simply flows. That means there is nothing that stops here. Right? That is why it is called a frictional slider. Is that clear? So now the deformation in this rheological model sort of represents the elastic perfectly plastic model, wherein the sigma is given by E times epsilon as long as sigma is less than or equal to sigma naught, because until then there is no frictional slider that is coming into picture. So that is why sigma is equal to elastic modulus E times epsilon until sigma is less than sigma naught. The moment if you have, so that means corresponding to that sigma naught, let us call this is your epsilon naught, that is equal to sigma naught by E. So until your epsilon, as long as epsilon is less than sigma naught by E, you can write sigma is equal to E times epsilon. But the moment epsilon becomes greater than sigma naught by E, that means to the right of that, then sigma will not change. Sigma remains sigma naught. That is what this equation is all about. So in this, what is happening is, so the total strain in the material, for example, if you are here, there is total strain that is in the material is elastic strain plus plastic strain. Okay. What is elastic strain? That is, suppose if you are here, this is my elastic strain, and whatever balance is my plastic strain. So sigma E is sigma by E, or sigma naught sigma by E plus epsilon P. When this is, sorry, epsilon is greater than sigma naught by E. When epsilon is less than sigma naught by E, epsilon P is equal to 0. Plastic strain will be 0, and hence epsilon is purely elastic strain. Is that concept clear?
Yes, sir.
Or is there any question there? Maybe I will write it here so that so you have a rheological model which is right, and to that I am applying some sigma, or you are applying epsilon, not sigma. You are applying epsilon, and then sigma is the outcome of that. And this guy has an elastic modulus of E, right? So now what we are saying is this guy represents, this is a rheological model that represents elastic perfectly plastic material, where on the x-axis you have strain, and the slope of this guy is E, right? So up to here is elastic. So elastic, what I am saying is sigma is equal to E times epsilon if epsilon is less than sigma naught by E, or sigma is less than sigma naught. Both of them are equal. Within this regime, that is what I am talking. Now suppose if I am here, if I am having a strain of that, in this scenario, you can see that sigma cannot be greater than sigma naught, right? The moment sigma becomes greater than sigma naught, this will slip, and then it cannot, then you will have deformation. Some of it will be permanent deformation, some of it will be elastic deformation stored in the spring, right? So now your total strain, suppose if you are at this position, that is my total strain, epsilon is equal to, I can write this as epsilon elastic plus epsilon plastic. How do I find out epsilon elastic and plastic? So if you do the unloading, right, I am coming up to here. So this is what is my, this part of strain is recovered, and this part is permanent. So this is my plastic strain, this is my elastic strain, right? So the total strain is equal to epsilon E can be written as, let us say that is sigma, which is sigma naught in this case. So I can write sigma by E plus epsilon P, where sigma is, what can I write? Where sigma is, sorry, where not sigma, where epsilon is greater than sigma naught by E. If epsilon is greater than sigma naught by E, I can write total strain is equal to sigma by E plus epsilon P. Right? Is this clear? Any questions?
So basically here, if I go beyond that, the value of sigma 0, sir, then as you told that it will start slipping out, right, sir?
Correct.
So if the slipping is happening, then there will not be further strain develop in the system.
Slipping is nothing but strain, no? It is deforming, no?
Okay. Noted. I got it,
Yeah.
sir. Now, fine. It's fine, sir. The question is okay. Thank you.
Yeah.
Sir,
So
one question.
now, yeah, please.
It should be less than equal to, na, sir? Then
Which one?
the first one.
Uh,
Sigma equal to if epsilon, because at exactly at sigma 0 you will not have the slip, right? If
at
it
sigma
crosses,
0, you will not have slip. Correct. Yeah. You are right. Thank
okay.
you.
Okay.
Yeah. And now you have next one is elastic and linearly hardening. What is the meaning of that? You have elastic, okay, and then linearly hardening. Earlier it was, if you look at the previous one, that was like that, right? Now this is linearly hardening. Okay, and the slope of this fellow is E, and I can call the slope of this fellow to be some delta E. So how do I model this rheological thing? All right. So now let's look at the rheological equivalent of this. So if you look at this fellow, this is, let us say, sigma naught. All right. What can we say? Let us say this is some sigma at some sigma. Right. What can I say about delta epsilon? Delta E. The slope of that line is sigma minus sigma naught divided by epsilon minus epsilon naught. Let us say corresponding to that, you have epsilon naught, sorry, epsilon. Corresponding to this, I have epsilon naught. Can I do that? Slope is nothing but y2 minus y1 by x2 minus x1.
Yes.
Okay. Now we can write when if sigma is less than or equal to sigma naught, then what can I write? Sigma is equal to E times epsilon. Is there a problem?
Right.
That is fine. Now let us write for this fellow. For this fellow. What can I write? For sigma, if sigma is greater than sigma naught, what should we write?
Your total strain will be a mix of plastic plus elastic. So
Yeah.
so the elastic one will follow sigma by epsilon.
Epsilon E plus epsilon P. Right? So what can I write? Sigma is equal to?
It's basically sigma 0 plus the slope of that into x.
So I can unload it like that, no? Right? I can unload this fellow like that. So what can I write? Epsilon E can be written as sigma naught by E. Can I do that?
Yes.
And epsilon P can be written as sigma minus sigma naught. That is this value, right? That is my epsilon P. That is epsilon E. What can I do that? Epsilon P. If I extend it up to there,
by delta E.
Sigma my, so what happens? Let us look at this fellow carefully. Epsilon E is, can I write it delta if I take this triangle, right? How do I take that? So let me use on another graph. If I say this is y, so this distance is how much? What is sigma minus sigma naught by delta E?
Epsilon minus epsilon naught.
Epsilon minus total epsilon minus epsilon naught. That is not epsilon P?
No.
Huh? Epsilon naught is your elastic strain, no?
But the unloading follows a different path. So
Unloading follows it will be same slope as this. This will have same E, no?
okay.
Yeah? Do you agree or not?
Yes, sir. I agree.
So the way that you need to see is here this is sigma naught by epsilon naught is equal to sigma naught by epsilon naught is equal to, because they are similar triangles, sigma by epsilon E, isn't it? Because epsilon E and epsilon naught are same, so sigma is equal to sigma naught. So you can do this comparison. So all that I'm trying to say here, this can be written as sigma naught, sigma minus sigma naught by delta
Epsilon
epsilon,
delta E.
delta E. So now I can say the response of this rheological model. This is, see what we have said, this functional response of any stress strain curve can be written as epsilon is equal to a function of sigma, or sigma is equal to some other function of epsilon. So in either way, this is what we call constitutive response. For different material models, we need to find out what this constitutive response is. So now for a elastic, linear elastic and elastic and linearly hardening material, I could have written epsilon is equal to sigma naught by E by plus sigma minus sigma naught by delta E. Okay. So now if you carefully observe what is my delta E, how do you calculate? So if this can be seen as sum of this rheological response can be seen as, it is as sum of the elastic strain in a spring E1, right? Or this can be written as an elastic module E1 and plastic strain or sliding strain in another spring whose modulus is E2 and sigma naught. What do I mean by that? If I draw a rheological model, now if you apply a sigma or corresponding to that sigma, you will get some epsilon. Then you can see that this delta epsilon as an effective strain that comes from these two models, right? And you can write your, in this equation, if you say E is equal to E1 and delta E is equal to E1 E2 by E1 plus E2. If you do that, then you have this rheological model represents this kind of a linear hardening model. So what you have is initially when you will have one pure elastic response is given by E1 and plastic slipping happens in this parallel model. And that is what is represented in the linearly hardening model. Similarly, next you have
Sir,
Quick question, sir.
in the background,
Uh,
very sorry. Just if you go up. Yes, sir. Yes, sir. So here, sir, E0 is very like visible that whatever strain we are getting because of sigma 0, that is E0. That is for sure. Now, secondly, the second parallel line to sigma 0 line is basically when we are like unloading the component. So the E remains same, and hence it is falling. Suppose if we name that point as C, sir, suppose for time being. I'm sorry to tell you, sir.
so say again.
Like if we just if we just give it like the point a name like A or something like that.
Where
Like E0 is defined, sir, suppose. That is suppose that the O for time being, I'm telling you, sir.
epsilon 0, you mean?
Right, sir, right, sir. That is suppose O for time being.
This is O, okay.
Okay, next is O dash, sir.
Where
Where the unloading is happening, sir. Like the slope, like
this is
the
O
same
dash.
slope of the E, which is like O dash, right? And this is the total strain that I have. So plastic strain will be O dash, right? So if I'm not wrong, right? Or it will be like
No.
from origin to this.
No. So if you let us look at this, let me draw this figure again for you.
Okay.
Let us say you have a stress strain response that is linear elastic and a linearly hardening model. Okay. Now that is my sigma naught. Okay. And this is my slope E1 and this is my delta E. Okay. Now if I am loaded the specimen beyond yield point up to a value called sigma dash. Okay. Now if you are unloading the specimen, what happens is it will have same slope as the loading specimen, right? So it will now unloads up to this point. Is that clear?
Yes, sir, clear. That is clear.
Initially, when you are, let us say you have not unloaded, but you have loaded up to here. What is the strain that you will see in the material? Epsilon 1. Epsilon
right,
dash
sir.
is the total strain, or epsilon. I call it as that is the total strain. Correct?
Right, sir.
When you say epsilon total, it will have some elastic component and some plastic component.
Right.
What is the elastic component? That is recoverable. So when you
Right,
unload this specimen, what is the strain that is recovered? That is the elastic component. Whatever is the strain that is remaining, that is called plastic strain. Okay. So when you have started from epsilon total, you have unloaded. Let us call this as epsilon 1. Okay. So that means after unloading to zero stress, are you coming to zero strain?
No.
No. So after unloading to zero stress, the strain, which is called residual strain, is epsilon 1. That means no matter what, when you completely unload, even when you come to the stress-free state, you got this epsilon 1. This is what we call residual strain, or this is also called plastic strain. So instead of calling epsilon 1, let me call it as epsilon P. Okay. Now the
Yes.
total strain can be written as, from here, this is zero strain. This magnitude is epsilon P plus whatever has been recovered. This from here to here you came back. That means this part of the strain is recovered. That I am calling it as elastic strain.
Right, sir.
Okay.
Right, sir.
Yeah.
So epsilon minus epsilon 0 is equal to epsilon P that we wrote in the previous equation that we have in the like what I mean is epsilon minus epsilon 0 is epsilon P. If you go up a bit, sir, in your page. Okay, so here what you have written is like we have just deleted that. So epsilon minus epsilon 0 is equal to epsilon P. That is the formula that we written. We had written. So sorry.
Here.
Uh,
Epsilon is equal to epsilon E plus epsilon P. That epsilon is total strain.
Sir, one small question here, sir. That
Yeah.
epsilon E also, should it be sigma 0 by E or sigma dash by E? Because it's a new set now.
We
right?
have to calculate now. Now let us do the calculation. Okay.
Okay. Okay.
So how do you calculate epsilon P? You need, this is epsilon E. So if you know the total strain, so epsilon E plus epsilon P is what you are getting, right? So let us say, what is the slope of this line? Let us say that is E1, right? So if you know E1, what is, this is a right angle triangle, isn't it?
Yes.
Is that a right angle triangle or not?
Yes, sir. Yes, sir.
Yeah. So this distance sigma 1 divided by epsilon total minus epsilon P is equal to E1.
Yes, sir.
Yeah.
Yes.
That implies
Sigma 0
epsilon
by
T epsilon E is equal to sigma dash by E.
Right. Yeah.
Right? So that is your elastic component. What is the plastic component? So plastic strain is total strain minus
Epsilon E.
epsilon E. So now coming to the total strain, you are writing this equation. If I write, if I know what is the equation of this line, by the way, the equation of this, say, let us say OAB. What is the equation of line AB? The equation of line AB is sigma dash minus sigma naught. Can I say that?
Yes. Yes.
Yeah.
By
Yes.
epsilon total
minus
minus
epsilon naught.
this is epsilon naught is what? I will tell you what is epsilon naught. Epsilon
sigma,
naught is
sigma 0 by E1.
E1. Keep that in
Yeah.
mind.
Yeah.
Is equal to delta E. That is the equation of this line, isn't it? Equation of line AB is that. Do you agree or not?
Yes, sir. Yes.
Yeah.
Yeah.
So now sigma dash, so minus sigma naught is equal to delta E times epsilon T minus epsilon naught. What is epsilon naught? Sigma naught by E1.
Yeah.
Right? That is delta E times epsilon T minus sigma naught by E1 times delta E. That is sigma dash plus sigma naught. So what can I write? Sigma dash is equal to 1 minus sigma naught, sorry, 1 minus delta into sigma naught. So 1 minus delta means delta E. 1 minus delta E times sigma naught. 1 minute, sigma naught by E1 times delta E So everything, let me write it in terms of sigma naught. So what can I do? Hmm.
Multiply and divide by sigma naught.
1 minus sigma naught times. Okay. Let me take sigma naught common. 1 minus delta E by E1 plus delta E times epsilon t. That is your stress at any point. Correct? All of you agree with that?
Right, sir. Yes,
Yeah.
fine.
So now the total strain at any point is what? Epsilon E. What is this? We write epsilon E sigma dash by E1. That is elastic part, no? Plus plastic strain. What is that plastic strain that we have written? One minute. Let me redo this fellow. So that is sigma dash is this one. Okay, sigma dash. Yeah. What is this distance? The distance will be what? The distance will be, can you compute this distance? Because this is epsilon naught and that is different from epsilon E. Please keep in mind. What is that distance?
Total minus epsilon naught.
Epsilon total minus epsilon naught.
No. In terms of sigma dash and all. So that distance can be sigma dash minus sigma naught. This distance is sigma dash minus sigma naught, no? By epsilon t minus epsilon naught, isn't it? This distance is sigma dash minus sigma naught divided by epsilon t minus epsilon naught. This is epsilon t minus epsilon naught, sorry. Yeah, that's what we got. That is the equation of that line. So epsilon t minus epsilon naught. Yeah. Yeah. Yeah, epsilon naught. That's what we got it. Okay. I will look into this and then get back to you on the actual this equation. I will maybe I'm missing something. Maybe we'll move on. I will look into it and get back to you on this. Okay.
Yes, sir. Sure. Thank you.
Sure, sir.
I think I made somewhere some mistake I'm making, but let me derive that and get back. Okay. All right. So now there is the third one, which is basically elastic power law hardening. So what do we mean by elastic power law hardening? It is basically your relation is sigma is, so this is like this. You have a linear elastic response followed by a power law. That means this is some h times epsilon power n sort of thing. So you can write sigma is equal to E times epsilon for sigma less than or equal to sigma naught, and sigma is equal to h1 epsilon 1 power n, h1 epsilon power n1 when sigma is greater than or equal to sigma naught. Okay, and at sigma is equal to sigma naught, E epsilon is equal to h1 epsilon power n1. So here n1 is called strain hardening exponent, and h1 is coefficient.
Why greater than or equal to sign is convention? Like, is it only
Because
greater
at this
than?
point there should be continuity, no?
Okay. Okay.
That's why. Okay. So on a log plot, this looks like a straight line. Just to make sure that you understand that this you we have seen that no sigma is equal to s is equal to n power b. It is very similar to that. So here, what happens is your the power law relation will becomes a straight line. So suppose if you plot on a log plot, these things will this one also look like a straight line, and this guy is anyway a straight line, and then you will be able to talk about it. There is another model called elastic Romberg Osgood model. What does this do? This says, so here you have written epsilon power n, right? This epsilon is your total strain. But Romberg-Osgood model does a little different. It says sigma is equal to E times epsilon for sigma less than or equal to sigma naught. Sigma is equal to h1 times, instead of epsilon, it will only written plastic strain epsilon p power n for sigma greater than or equal to sigma naught. So this is what we call Romberg-Osgood model, wherein you actually raw power law relation is only on the plastic strain. Regular power law hardening, it will this epsilon is total strain. That is the only difference. There are two different models, and we people can use any combination of that. But as you have seen, all these are nonlinear models, right? So this nonlinear model, this is a power law model. If I zoom in, so for example, let me draw this for you. This is a power law, right? Now, this power law model can actually be, if you zoom in, I could say that this is one straight line, this is another straight line, that is another straight line, that is another straight line, and so on. That means I can actually simplify a power law model as a series of lines, isn't it? Each one having a different slope. Each one having a different slope. So that kind of a thing is already done in the literature. You can see if you look at this fellow, this is what we call a nonlinear hardening. If you have a not a power law hardening but very nonlinear hardening, that regular nonlinear hardening model can be represented by a series of linear hardening models. So here, as we have seen in the previous this thing, so this sort of represents this linear hardening model, but if you add them in series, you will be able to represent a nonlinear hardening model like that, right? Wherein for a linear hardening model, as we have seen, if sigma is equal to epsilon sigma naught by E1, this is your E1, and sigma delta to E, delta 3E, delta 4E, and so on, wherein E2, E3, E4, whereas delta to E will become E2, E1, delta E2E is E2, E1 by E1 plus E2, delta 3E will be E3, E1 by and so on, and then you will be able to represent this entire strain constitutive relation using this power law, series of power law, series of linear hardening models. So these are the various rheological models that one can use. The spring dashpot model, not dashpot, spring friction slider models in order to represent the plastic deformation. Please note that here nowhere we are using dashpot. We are using a friction slider model because a dashpot will represent some time dependent phenomena. Here we are talking about a plastic deformation which is not time dependent, that means strain independent phenomena, and hence we are not using any dashpots. When you have a viscoplastic deformation, then you will use dashpots in your model to represent the viscous dissipation. But otherwise, a spring and a friction slider will be able to completely represent a regular plastic deformation that we have. And this is something that we have studied in the previous static failure theories. When your strain, the equivalent strain, this is our von Mises strain, when this becomes equal to the yield strength of the material in a 3D state of setting, that is when the plastic deformation takes place. So now corresponding to that, one can compute something called effective plastic strain. That means at that particular strain, what is the effective plastic strain that one can compute by knowing corresponding to sigma 1, what is the plastic strain, epsilon P1, epsilon P2, epsilon P3, and one can compute the effective plastic strain given by root 2 by 3 and this. And then the total effective strain, because it's a 3-dimensional setting, until now we are only talking about 1-dimensional scenario. But when you talk about 3-dimensional setting, then your total strain, total effective strain is given by effective elastic strain plus effective plastic strain. This effective plastic strain is this, effective elastic strain is effective stress by elastic modulus. Is that clear? In a 3-dimensional scenario. Any questions here? So how do you calculate plastic strain? So your effective plastic strain epsilon P1. So for example, if is your effective strain versus effective plastic strain plot, and your EP, this is what we call plastic modulus, is given by sigma bar by epsilon P bar, and you can calculate your plastic strain x direction, y direction, z direction, very similar to your Hooke's law. You just need to replace E with plastic modulus. What is plastic modulus? On a sigma bar epsilon bar P graph, if at any point, if you want to find out the plastic modulus, you just try a straight line. The slope will give you the epsilon P, EP. That is the ratio of sigma bar to epsilon P bar. That is what is your EP. Okay. So that means your plastic modulus changes with increase in plastic strain. If you are calculating plastic modulus here, this slope will be different compared to plastic modulus here. As you can see, the slope is changing, and hence the plastic strain, plastic modulus keeps changing, keeps reducing as you increase the plastic strain. So the epsilon x can be written as epsilon elastic x plus epsilon plastic x, and then epsilon elastic x is this, epsilon plastic x is this. Just everything else is same except that your plastic strain E is replaced by plastic strain, nu is replaced by 0.5. Why? Nu is equal to 0.5 represents incompressible scenario, and when the plastic deformation is happening, there is no volume change. Because there is no volume change, that is what is called incompressible response, and hence nu is replaced by 0.5. You please pay attention to that. So if you can plot an effective stress strain curve like effective strain, effective plastic strain, effective stress. Similarly, you can plot an effective stress strain curve. So what is that? How does it look? Let's say the uniaxial stress strain curve for a given material is given by epsilon 1 is equal to f of sigma 1. For a 3D state, the effective strain is equal to f of sigma bar, that is effective stress strain. So how does this effective stress strain curve look like for a case of plane stress? So we can actually plot the effective stress strain curve for a state of plane stress. Can you try to think about how one would plot an effective stress strain curve for the state of plane stress? What is plane stress?
Z component would be 0.
Yeah, the third component will become 0, right? So let us try to do that. I will. So let us say let us say the axes are chosen in such a way that your principal stress sigma x is along sigma 1 and sigma y is along sigma 2. That means principal directions. And always, if that is the case, there will always be some linear relation. Let's say sigma 2 is equal to lambda times sigma 1 without loss of any generality, some constant. And sigma 3 is equal to 0.
Sir,
Then,
the notepad is not visible. It is stuck with something.
is it? Okay, let me stop share. Now it is visible?
Yes, now it is.
Yes, sir.
So you have the effective stress can be written as square root of sigma 1 minus sigma 2, sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. That is what is our on stress. From that, if you write sigma 1 and sigma 2 is equal to lambda times sigma 1, you can always write, right? Sigma 2 is lambda times sigma 1. Can you do that or not? This becomes 1 minus lambda plus lambda square. And so the total strain now, the total strain in the direction of sigma 1 will be, so I will call it as epsilon 1, epsilon E1 plus epsilon P1. Elastic strain plus plastic strain, right? So the elastic strain can be written as in 3D sigma 1 by E times 1 minus nu lambda, because epsilon elastic strain is sigma 1 by E minus nu by E times sigma 2 plus sigma 3. Now sigma 3 is equal to 0. That will become sigma 1 by E minus nu by E. Sigma 2 is lambda times sigma 1. That is equal to sigma 1 by E times 1 minus nu lambda. That is what we are writing it here. Right? Similarly, plastic strain is equal to, you can be written as sigma 1 epsilon P bar by sigma bar into 1 minus 0.5 lambda. Because you are here, you basically, I will tell you what it means. Epsilon P1 can be written as sigma 1 by EP into 1 minus 0.5 lambda. Because E is replaced with EP, nu is replaced with 0.5. That is what your plastic strain is. And what is EP? EP is nothing but sigma bar by epsilon P bar. That is your EP, isn't it? Because when you have plotted sigma bar versus epsilon P bar, effective plastic strain and effective strain, let us say that is the curve. At that one, this is your epsilon EP, plastic modulus. So by replacing EP with this fellow, that means epsilon P1 will become sigma 1 epsilon P bar by sigma bar into 1 minus 0.5 lambda. That is what I have written. Right? Now I can write epsilon P bar plastic strain, effective plastic strain is effective total strain minus elastic effective strain, that is sigma bar by E. And now epsilon bar can be written as some function of sigma bar minus sigma bar by E. That is your effective plastic strain. Right? And now if you look at epsilon 1 is equal to epsilon E1 plus epsilon P1, right? So epsilon E1 is what? This fellow. So that means 1 minus mu lambda by E times sigma 1, right? Plus epsilon P1 is 1 minus 0.5 lambda, that is this fellow, by sigma bar, 1 minus 0.5 lambda by sigma bar times sigma 1 into epsilon P bar, right? Because there is an epsilon P bar here. That implies that is equal to 1 minus mu lambda by E times sigma 1, right? Plus 1 minus 0.5 lambda by sigma bar times sigma 1 into f of sigma bar, that is epsilon P bar, is equal to minus sigma bar by E, where you can obtain sigma bar, where sigma bar is given by this equation, is equal to sigma 1 root 1 minus lambda plus lambda square. So you plug in f sigma bar and then you will get this thing. So if you have any, for any uniaxial curve where epsilon bar is equal to given by f of sigma bar, and for any biaxial straight with lambda, one can find out what is your epsilon 1, epsilon 2, epsilon 3, and then you will be able to identify what is the effective stress and effective strain. Okay. We will look into it in detail in tomorrow's class, and then we will move on to. So the reason why we are looking at plastic strain carefully, because we need to understand how this plastic strain can be accommodated in your fatigue calculation. So this is something that I would like you to carefully pay attention to. Okay. All right. I think with that I'll stop here, and then we'll meet again tomorrow at the same time. Thank you.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.